So maybe just by way of introduction, Daniel is also a very broad mathematician. He's well known for really interesting work in algebraic geometry. And I was really interested to see this work that he's talking about today, which is about guiding deterministic algorithms using machine learning. And this is a topic that we haven't really covered so far in the seminar. So we're very much looking forward to Daniel's talk, and thanks a lot for speaking to us today.
Yeah, thank you so much for inviting me. And I did this project 2 years ago, but it's the first time that I'm giving a talk on it. So I should start by saying, so this is the project finished in 2020. We went into this ICML proceedings, which is like a machine learning conference. And it was with Mike Stillman, who's here at Cornell. He's an expert in computer algebra systems. He's the author of Macaulay 2, or one of the main authors of Macaulay 2. Dylan Pfeiffer was a student of his. I sort of got interested in this machine learning stuff. A friend of mine in grad school at Berkeley founded a machine learning startup shortly after and kind of roped me into doing some consulting work, and I started to learn about this stuff. And while it was a self-driving car startup, but while I was doing that, it was pretty interesting work, but I couldn't help daydreaming about, my first love, which was algebraic geometry. And so I ended up with this weird idea for a mashup project where we try to apply some of this machine learning stuff to a really important question in algebraic geometry. This is the project that grew out of that little inspiration. So, and I should say these slides have sort of been adapted from a talk that Dylan gave on this paper way back when. He was really like, I would say, the driving technical force. He did most of the coding on the project, and I was sort of involved, but I did not do most of the coding. But I was involved with a lot of the visioning of the project and the actual trying to figure out how to get the thing to work, as was Mike. So anywho, Dylan has gone on now. He's not in academia anymore. He's gone on to work in mathematical finance. So he made good use of the skills he gained on this project. Now Mike and I are still talking and working with new students and are hoping to kind of push the project forward. So that's the status of things. Okay, so just to give a bit of an overview, because I think I'm not sure how much background people have with this stuff. So Buchberger's algorithm is really fundamental for doing computer algebra with polynomials and with ideals and polynomial rings. So lots of questions that you might ask, from the most basic question of, if you have a polynomial ring and you have an ideal, does this particular polynomial sit in that ideal, to questions about the dimension of the variety defined by the vanishing of some set of polynomials, or the Hilbert function of some homogeneous ideal, something like that. Many of these algorithms come down to first computing a Grogner basis for an ideal, and then using some kind of, basically allows you to reduce it to a much more combinatorial question usually. And so this Buchberger's algorithm is a way of finding Grogner bases for an ideal. And we're going to go over the algorithm in detail. And basically it depends at several points on human design decision heuristics. And so, well, the question is, can we, and they're heuristics, really. Even Mike Stillman, one of the co-authors on the paper, who's been doing this for decades, there's lots of rules of thumb and little tricks and little tools of the trade that are really just available to experts. So the question of this project is, can we use reinforcement learning to try to do better with these algorithms? So these things that are like tricks that have been passed down from one master to the next, can we actually take more of a data sciencey approach and replace these heuristics with learned decision strategies? Yeah, so the main contributions to the project. So basically we looked around. I mean, as far as we know, not a lot of people have studied this problem as a statistical problem, or even, especially not from the perspective of machine learning. So there were some points, maybe I'll mention people who have used machine learning to do things related to Buchberger's algorithm, but really the study of how can you improve this algorithm by thinking of it as a data science problem where you have some distribution on ideals and you want to kind of optimize the output, in some average sense. We've not seen anything in the literature like that. It's possible that people that do computer algebra systems do think about the problem that way. But, like I said, Mike designs Macaulay 2, and that's not the way that he traditionally thought about the problem. So this is sort of new in that way. And as we'll get into in a little bit, basically there's the problem itself has all these little twists and turns that make it really difficult. And so one thing that we did which I think is maybe useful for follow-up research, is to try to narrow it down a little bit. We focus on a particular subdomain that captures a lot of the difficulty of the problem, but avoids some other difficulties which feel less fundamental. I'll explain that a little bit as we go too. Then the other thing is just the very empirical. We actually were able to train a model in this particular domain that we were studying that does better than all of the known state-of-the-art strategies. And it even actually, we were able to learn from looking at what the model does, we were able to learn a new strategy, which is a natural enough guess, but is not one of the standard ones that Mike was aware of. It's not one of the standard ones that's used. So we sort of discovered a new simple strategy through the machine learning thing, which I think is kind of an interesting little twist of the story. Okay, basically Grogner bases, as I mentioned, there's special sets of polynomials, and they're useful in many situations. But, you know, I mentioned a few theoretical cases, but actually they come up quite a lot in you know, applications to a mathematician. An application is just another theorem that uses your first theorem. But actual, like, you know, engineers and stuff use Grogner bases. It's sort of interesting that maybe not, I don't know who the backgrounds of people, but for me, this is kind of a novel experience to be doing research in something that might actually be useful for creating a robot or something like that. So that's pretty cool.
I was just wondering, does your model sort of perform better on some types of ideals than on others?
Yeah, well, I'll tell you about that. We'll get there. Yeah, yeah. Sorry, it's going to be a little bit slow, but yeah, we'll get there in about an hour. In the domains in which it's trained, it does better. That's the sort of most correct answer. Like you train it in a domain, and then it does better in that domain. But it's very difficult to train it in the domains that involve really hard ideals. It's difficult to train it in really hard domains, and it generalizes okay, but there are some limitations to how it generalizes. So, you know, it's more of a proof. This whole project is more of a proof of concept, I would say. This is not going to go into a performance computer algebra system anytime soon, but we'll talk about some maybe future directions.
Yeah, thank you. Yeah. So this means it's not sort of, I shouldn't think of this as an out-of-box solution where I just stick in my ideal, but I could actually, if I have ideals from a certain problem class, then I could train a model on these ideals and hope that for other applications in the same domain, it would perform better.
Yeah, so that's true. That's true. Yeah, that's one way. But I mean, I'm sort of optimistic. I mean, the ultimate goal would be to have a sort of out-of-the-box solution. It's a philosophically interesting question because these machine learning models, I mean, typically they'll do very well in the domain in which they're trained, but then, you know, domain adaptation is what they call this thing where you try to train it in one domain and use that model to do it on another domain. And that's like traditionally a very difficult problem. But you might think that there's actually some underlying structure there. You know, we do have selection strategies, simple heuristics that work pretty well in all domains for this particular problem. And you might wonder if this is not, you know, this isn't actually a statistical problem. Maybe there's some actual structure of the way that polynomial, you know, maybe there's some actual good strategies that this thing might learn that would transfer across domains, because, you know, the domain adaptation problem has to do more with, like, you're training on one set of natural images and you're comparing, you want to take this model and apply it to a different set of natural images, and it really is a statistical question to begin with. Here I think the big empirical question, which is still open, is, are there like deep truths about Buchberger's algorithm that we can learn with reinforcement, that we can sort of get to via reinforcement learning, that are too complicated for a human being to figure out on their own? And that I think is open still. Okay, so the basic, just to establish some context. So the basic question you might ask is, does this system of equations have a solution over C? If there are polynomials so that you can write one, the constant polynomial, as a polynomial combination of these two, then of course there are no solutions, because you get 0 equal, you know, in other words, you get 0 equals 1. And then the Hilbert-Snell-Schellensaatz gives the converse to that. So a very, very basic question you can ask about geometry is, does the system of equations have a solution? And the answer amounts to figuring out if h equals 1 is, yeah, so the question is h equals 1 in the ideal generated by this set of polynomials? All right, so one thing you could try to do is, you have your set of generators you have some, which I like to think of as a system of equations. You have your set of generators for the ideal, and you can do this multivariate division algorithm. This is not quite specifying it. The point is that you take your polynomial h and you sort of write it, you take your generators and you write it, these q1s through qs's are monomials, and they're chosen so that at every stage, q1 f1 exactly matches the largest term of h. And so what's left is then some remainder, and then you take q2 f2, which exactly matches the highest term of the remainder, and so on and so forth until you get to some remainder r that's smaller than whose lead term is smaller than the lead term of any of the generators, and then you can't continue this anymore. It's not actually a well-defined function. It's sort of an algorithm, and it depends on the actual choice you make, which of the generators to try to use to cancel the highest term of h. But in any event, if this remainder is in 0, then you know that h is in the ideal that's generated by these polynomials f. But the converse is not true. So in other words, you can have h that happens to be in the ideal, but when you run this algorithm, it does not reduce to 0. You end up with a non-zero remainder. So one way to define a Grogner basis is a Grogner basis is a set of generators for the ideal, such that the remainder that you get when you run this reduction algorithm is guaranteed to be 0 if h is in the ideal. So that's a Grogner basis. There are other equivalent definitions. So to make this precise is a funny, you have to say what I mean here. I had this lead term of r is smaller than any of the lead terms of fi. So, that has an intuitive meaning maybe, but to make that precise, you have to take you have to say what you mean by the lead term, or you have to basically have a total ordering on the set of monomials. This is called a monomial order. And we're just always going to use what's called Grevlex. Basically, if you have two monomials, the one with the larger degree is larger in this order. And then after that, you look at the exponent of xn, and smaller exponents for xn is larger, means the monomial is larger. And then if it's a tie in the exponent of xn, you go to xn minus 1, and smaller exponent means a larger monomial, et cetera, et cetera. So this is the monomial order. Just show this here for illustration, that x1 is bigger than x2, in this ordering. So, and the key property, this theory of Grogner bases works for any monomial order. The key property is that if you have a less than b, and you multiply them for two monomials, and you multiply them by a third monomial c, then ac is less than bc. So the lead term of f is the term of f with largest monomial, including the coefficient with respect to the given ordering. It's nice to leave this ordering as a sort of parameter of the problem. There's some kind of elimination problems and things like that require like variable elimination that requires specific monomial orders, but other things, like I mentioned, computing the dimension or the Hilbert function or any of these things, all you really care about is that you have a Grogner basis in some monomial order. And empirically, this Grevlex ordering that we're using works pretty well. And so all of our experiments use Grevlex.
I'm more an applied mathematician, and for example, singularity theory. So naturally, you actually would have weights on the monomial, like structure. So it's actually, in our case, more natural to have a weighted basis than actually like that. So is it easy to adapt the algorithm then in this case?
Yes, it's invisible. The monomial order in the actual code, the monomial order, I think we use this package, SciPy. No, not SciPy. We use a symbolic compute, SymPy. We use a package, and built into SymPy, I think the monomial order is built into the ring class. So it's all completely invisible. The code would run with any monomial order, but I can't vouch for how well it works. But I wouldn't expect it. I wouldn't expect anything else, anything drastically different.
I have another question as well to add this. So you said you mainly used Grevlex for what you did. When sometimes, I thought sometimes, some monomial orders perform much better than others when one tries to apply Buchberger's algorithm. And so did you sort of think about also how could I learn sort of a best monomial order for the ideal that I'm working with?
Thank you for that. Thank you. So there actually is, this has been done a little bit. There was a paper that basically you show it generators the ideal, and it tries to guess a good, I think in that case, good weighted monomial order. Good in the sense that the algorithm will run efficiently on it. So that has been investigated, but not by us. Yeah. No,
it's just good to know that it's been done.
Yes, that has been investigated. Yeah. So the way that Buchberger's algorithm goes is that you have given two polynomials, you form an S polynomial, which is exactly it's defined to be something that exactly cancels the lead term of both f and g, and it's guaranteed to lie inside the ideal. So Buchberger's criterion says that if you start with a generating set for the ideal, then it's a Grogner basis if and only if when you reduce these particular S polynomials for every pair, you get 0. In our example, in our previous example, we had these two generators for our ideal, and I've underlined the lead term so you can see it visually. So basically, when you try to form the S polynomial, you multiply by y here and x here so that the lead terms exactly cancel, and you're left with something that when you try to reduce it, you get y cubed plus x. In fact, there's no actual reduction here. It's already y cubed plus x. There's no way to cancel the lead term with these two generators. So Buchberger's criterion is not satisfied, and we add y cubed plus x to the generating set, and then you can check that when you reduce now. Again, with Buchberger's criterion, we check that the S polynomial for these two generators does not reduce to 0, but when we add this as another generator, now that will reduce to 0. But now, if we add another generator, we have two more pairs to consider. We have to consider the S polynomial for this pair and that pair. But fortunately, they both reduce to 0. So when you add this third generator, it is a Grogner basis. And so the algorithm is basically to do what we just did in this example. You start with some original generating set, and then you start with a list of pairs. And then you just go through your list of pairs, and you select and you remove one of the pairs from the pair set. Then you compute this polynomial long division using the generating set. If you happen to reduce to 0, then you do nothing else. You just removed one of the pairs. That's great. The pair set gets smaller. And otherwise, you add this remainder, which, as I mentioned, is guaranteed to be in the ideal still, and you just add it as a new generator. And then you do this thing called updating the set of pairs P. So the basic version of the algorithm, there's no updating. You just remove this pair, and you add a new generator. And the only updating you have to do is to just add now a bunch of new pairs. So if the pair set had n, so if the generating set had n generators before, and now you add another generator, you get n new pairs. And then at the very end, so once the pair set is empty, once you've reduced all the pairs, then you have Buchberger's criterion and you have a Grogner basis. And so I've highlighted in blue here the choices that are involved. So you have the selection, so which pair you choose first, the order in which you choose the pairs. And then actually implicitly, I mentioned this, but in the reduction step, there's also a choice because there might be more than one generator whose lead term divides the lead term of the S pair. And so as you get, at every stage, you have a sort of to choose which generator to use to cancel the lead term. And that can affect how long the reduction takes, and it can affect the remainder and all that stuff. And then in the update step. So, and I'll mention that in a second. So, but these things can all affect the performance. So the number of iterations can become large. You can even get different size. You can end up with different Grogner bases or different size Grogner bases depending on the choices involved here. So there's even though the algorithm is guaranteed to terminate, there's quite a lot of flexibility with how it's actually implemented.
Is it entirely obvious that it terminates? Like, what's the easiest way to see that?
No, I don't know. That's the theorem. I actually don't know the proof of the theorem off the top of my head. But that's like that's Buchberger's theorem.
I see.
It's not obvious. Yeah, yeah.
Thanks.
Yeah, it's sort of crazy because it's like the heads of the Hydra. If you don't have a Grogner basis, then as your set of generators grows, you end up adding more and more and more and more pairs. Yeah, but it is guaranteed to terminate. Well, no. It's easy. Wait. The termination maybe is easy. Just because of like Noetherianness or something like that. Like you can't keep adding more and more and more generators. You're putting me on the spot, man. I think it's actually not hard to see the termination. I can't think of it off the top of my head. All right, so most work on improving Buchberger's algorithm focuses on this update step. So the idea is because one of the issues here at number 3 is that you have to add a whole bunch of new pairs every time you add a single generator. So the goal of a lot of research on improving performance has to do with, is it possible to skip adding any of those pairs? The most basic case in which you have a pair that's skippable is when you, just for simplicity, if you assume f and g have lead coefficient 1, then if the GCD of these lead monomials of f and g is 1, then the formula for the S polynomial just simplifies to this. And what you can do is there's like a little trick. I can write 0, which is gf minus fg, in this funny way where I say it's the lead monomial of g plus lower order terms and lead monomial of f plus lower order terms. And I get an expression like this that says that the S polynomial is expressible, is equal to this thing. And if you think about it for a bit, the f prime and the g prime having lower order terms is basically giving you a recipe for reducing SF to 0 using only the generators f, g, and f. So it's almost like you don't even have to consider, in principle, when you're doing the reduction, when you're reducing the S polynomial, you can look at all the generators in your current generating set. But in this particular case, you actually don't have to look any further than f and g. It will be possible to reduce SF to 0 just using f and g. And so you don't actually have to do the reduction because it's sort of automatically is going to happen. And the condition here is that the GCD was 1. So that's an example of a kind of pair where it's a very simple criterion where you know that this pair will actually, the S polynomial for the pair will reduce to 0 using only the generators in that pair. And then there are more sophisticated criteria like this. So the Gebauer-Muller is sort of a similar thing using triples of generators from the generating set. And it gives a sort of criterion for when you know, without actually doing the whole reduction, that the S pair will in fact be reducible to 0. There's another class, these Fougere has for several decades has developed these algorithms kind of in some domains they're state of the art for this problem. And it also involves it also involves finding more and more sophisticated criteria for pairs that can be eliminated without actually doing the reduction, because the reduction step can take a lot of time in the algorithm. In this research, we put that aside because there's sort of there's a whole very developed literature on that particular aspect of the problem, and we focus on pair selection. So strangely, and this is, I'm sure someone will correct me but to our knowledge, most implementations, the selection step use pretty simple heuristics. So an example would be you look at a pair of generators in the pair set and you choose the one with if you take the least common multiple of the lead monomials of the two pairs, you take the one with the smallest total degree. We call that the degree strategy. The other one, there's one called, we call the first strategy, where you just choose the pairs in the order in which they appeared in the list. So you treat it like a queue. They're all very basic. So this is the question. So can we use reinforcement learning to develop more sophisticated pair selection strategy? I'm also skipping the reduce thing. That's another interesting question of, are there better strategies for more efficiently, if you have a generating set, to more efficiently reduce? We did not consider that too. There's really like a lot of directions of this problem. Okay. Just to, again, to continue to paint the picture here of what the problem is. So the number of generators in the generating set might grow. Sometimes you end up, if you make bad selection strategies, you end up with too many generators, so redundant generators. So that's a problem. But also sometimes it's unavoidable. There's a unique minimal, what's called a reduced Grogner basis. So none of the lead terms of one divide the other, of one generator divided the lead term of another generator. So that's actually unique. There's a unique reduced Grogner basis, and sometimes it can be very large. So you might not be able to help the number of generators growing, but still, as you're running the algorithm, it can blow up in several ways due to bad choices or otherwise. So the number of pairs can grow. We talked about that already. The number of terms in the polynomials can grow. And this definitely happens as you start to reduce, and you just end up with all this kind of random junk, and that can be enormously costly to be doing multiplying and adding these polynomials that have thousands of terms. And also the coefficients of the polynomials can grow. So that's if you're working over Q or something like that. So, which is fine. I mean, maybe you care about that and you're tempted to, and the whole fun of Grogner basis is that it gives you exact solutions. So it's nice to work over Q, but then you have this issue that the denominators can get enormous. Okay, so hopefully the number of pairs growing, we keep that in check with hopefully a good pair selection strategy. That's kind of our goal. For 2, the fact that the number of terms in the polynomials grow, we're going to restrict to binomial ideals. And I'll talk about that more in a bit. But the key property about binomial ideals is that if you start with binomial generators, binomials meaning just 2 terms, if you cancel their lead terms, you also get a binomial. So the S polynomial, if you start with binomials, will then be a binomial. And also when you reduce, it stays a binomial the whole time. If you start with binomials in your generating set and you run Buchberger's algorithm, will remain with binomials. And so at least some of this problem, some of the ways in which the algorithm can blow up are not an issue if you're just using binomials. So that's the, and then the other thing is this coefficient, large coefficients. We just fix that in the sort of usual way, which is take coefficients in a finite field of large characteristic, and then there are standard ways in computer algebra to sort of Chinese remainder your way. Either the question you're interested in can be answered in finite characteristic and then lifted to positive characteristic, or sometimes if you can use finite characteristic methods to actually find the Grogner basis in characteristic 0 as well. So, but anyway, it's pretty standard to say, well, we just work with this enormous prime field, finite field, and we'll just do the calculation. We'll just take integer coefficients, reduce mod that prime, and we'll just do the calculation there and hope that it works. I hope that it gives the right answer. So that's pretty standard.
Isn't there also some kind of trick that if you do things over 3 different very large primes, that you then basically know what happens in characteristic 0?
Yeah, that's right. There is a trick like that. So, yeah.
And I guess the other comment to number 2 is, I guess, this kind of a standard thing, right? That you try to understand the problem set for these kind of toric ideals that are in the set that you have there, and then maybe hope that this gives some general insights as well.
Yeah. Okay. So I have to discuss this a little bit just because it's kind of crazy, but the worst case complexity of this algorithm is atrocious. So there are bounds. So one way to think about that is to say, what's the maximum degree? If you take, as I mentioned, the unique minimal reduced Grogner basis, you can ask, what is the largest degree of a generator there? So when the Grevlex ordering in a Zariski dense open set in a suitable sense, in a Zariski dense open set, you can bound the maximum degree of the minimal reduced Grogner basis this way, which looks pretty good, except that you realize that doesn't really bound the size of the Grogner basis that well, because there's like, you get like an n times d to the n, basically, number of monomials that have degree less than or equal to this. So it's still like a ludicrously large number of monomials, but it's not as bad as so this is like with probability 1, you have some kind of bound like that. But then there are these really crazy examples, like this Mayer-Meyer example, where this is about as simple as it can be. So you have these homogeneous quadratic binomials, and the number of generators, the number of variables is 22n minus 1, and the degree of the maximal degree of a Grogner basis element has this doubly exponential behavior. And the reason why that's terrible for performance is because, I mean, you start with things of relatively low degree 2, you start with things of degree 2, but somehow there's no way you can actually find that generator without doing that many steps, because you're doing that. You start with a binomial ideal, and as you reduce, you sort of, you'll start to cancel binomials, and you get higher and higher and higher degree terms. But if you're going to somehow get all the way out to that degree, it's saying that you sort of you need a really, to do this, it's going to take a ton of steps to get there. So that's really the bad news for the worst case performance. And there are doubly exponential upper bounds too, but that hold in general, that are much worse than this upper bound. But in any event, it's known. The synopsis is that it's known that there are really bad examples where it's not even possible in principle to compute the Grogner basis quickly. But in practice, many of the ideals don't exhibit this doubly exponential behavior. And so this is the domain. I've sort of hinted at this, but the binomial domain, the domain where we should be thinking about this problem as a sort of test case for the more general thing, is so indexed by n, d, and s. So that's n variables. S is the number of generators, and d is the total. The binomials should have total degree less than or equal to d. And so, as I mentioned, this avoids the number of terms. Every polynomial you ever see will be binomial in the algorithm. The Mayer-Meyer example, luckily, is a binomial ideal, and so we do know that this domain captures this kind of worst case doubly exponential behavior. And it also is nice because it captures, when I say non-generic, I mean not complete intersection. So, other ways of parameterizing ideals, if you're sort of not careful, you end up parameterizing complete intersections, and in a lot of ways those are much nicer, including in the ways that are relevant to this problem. Those tend to be much nicer than non-generic ideals that are of interest in algebraic geometry. So this gets to that sort of philosophical question that I'm not sure that there's a good answer to, is what does it mean to have a random ideal? And so you have to think about, well, what process is your ideal coming from? I mean, the most naive thing, you'd end up with complete intersection, which is just not really capturing the right. Yeah, at least these binomial ideals they're not complete intersections. They can capture the bad behavior. And also, something like computing the image of a monomial map, you end up with these binomial ideals, and that's of interest in algebraic geometry. And there are even applications from that crazy list of applications I showed in the beginning that involve binomial ideals. So it's by no means like a worthless question, and it hopefully captures some of the difficulty of the problem and avoids some of the incredible difficulty of polynomials that involve thousands of terms. So, and this is just an illustration. When you sort of now think about this as a statistical problem, you can sample binomials just by sort of choosing choosing a distribution on the monomials of degree less than or equal to d, and then you draw two monomials from that distribution, and then you choose the coefficients uniformly at random because we're over a finite field, and that's how we sample. And then when you do that in this domain, NDS, I guess this is 5, 5, 5. So 5 polynomials of degree 5 in a ring of 5 variables. And this is what the number of polynomial additions needed in the algorithm looks like. So it has the distribution has this long tail. And that's kind of that's sort of what I meant when I'm saying that the typical behavior is clustered down here, but the worst case behavior is going down here. and that's contributing to, I don't know, some of the difficulty of the problem.
And so how does this graph change with the size of the field?
I don't know how it changes with it. We always use with 32003 or whatever. So I'm not sure. Yeah, that's a great question.
And are you just sampling using some uniform distribution on binomials or something?
Yeah, I think there are a couple. I'll specify that a little bit more. But we had three things. One is where you just do homogeneous binomials of degree d. The other is where you consider them like, every monomial of degree less than or equal to d, you take the uniform distribution on that. So the way this is sampled is you choose two random monomials, and then you choose random coefficients uniformly, and then that's your binomial. And so the question is, what do you mean by a random monomial? And for a random monomial, there's like sort of different things you might mean. So you could just do uniformly at random on the set of monomials of degree less than or equal to d, or you could, another thing we did is that we weighted it so that every degree less than or equal to d happens with the same probability. So the difference between those is that it tends to be, if you took uniformly at random, you'll get a lot more monomials of high degree, basically. Like most monomials have high degree. So I don't know. Then the results vary a little bit, both in terms of how difficult the problem is on average and in terms of how well our models are able to train it. So the ones that have more monomials of high degree tend to be harder. Having monomials of low degree appear just seems to make the problem easier.
I didn't get why there's a choice involved in reduce.
I didn't quite write it as an algorithm, but basically the way it is an algorithm, and you look at the lead term of H, and then you look at the lead terms of your generators. And for any generator whose lead term divides the lead term of H, you can choose to write it as a monomial times that, and then you cancel. But that's the choice. There might be more than one generator whose lead term divides the lead term of H.
Thanks a lot.
Yeah, so reinforcement learning is a sort of general paradigm to sort of understand and optimize decision problems that involve an agent interacting with the world. It has a long history in playing games, backgammon, chess, Go, and StarCraft, and flying helicopters, driving cars, controlling data centers, I don't know, you name it. It has a longer history than all this stuff with the neural networks. DeepMind is very notable for had like a lot of breakthroughs applying reinforcement learning techniques to solving these, like solving chess or solving Go. There have been some really famous examples, and I think just reading about that was part of what inspired the project, because when you think about it, there's kind of an aspect of Buchbergers algorithm which is a little bit like playing a game of solitaire or something like that. Like you sort of have to choose, and it feels very much like a game. And if the computer can solve Go, then it should be able to solve Buchbergers algorithm. Basically, the way it works, the model that you should have in your head is there's an agent and there's an environment, and the agent does an action. The environment is always in a state, and there's this kind of feedback loop. The agent chooses which action, then the environment processes the action and figures out what the next state is based on the action that the agent took. And then it updates the state, and it gives a reward and sends that back to the agent, and that then continues this kind of feedback loop. And the agent's goal is to maximize its return. So it's the sum of the rewards over the entire length of the game. And sometimes people include a discount factor too for discounting future rewards. But anyway, I should say that in the most general formulation of this problem, nothing has to be deterministic. So everything is a probability distribution. So basically you have this Markov decision process. It's the transition dynamics for the environment, and basically it's given a starting state and an action, you get some probability distribution over what the next state is and the reward that gets accrued to the agent in that turn. Basically, the environment implements this and then sort of samples the resulting distribution and returns that to the agent. I mean, in our examples, it's deterministic. So this is just a little bit of a overview of reinforcement learning, but for us, the environment is entirely deterministic. So, a sort of famous little example that you can just play, you can use OpenAI's Gym and start very quickly experimenting with this stuff. This cart pole thing, so it's a little, has a little simulated reality in there, and you get to slide the pole back and forth, and the goal is to keep it from flopping over. And you just get one, you get 1 point for every unit of time that the pole stays up. And so the goal is just to maximize your reward. The agent just tries to keep the pole within a certain angle for the longest period of time. Okay, that's a simple one. So the agent, the policy, is also non-deterministic, and it's sort of more essential that the policy be non-deterministic. And so basically, the policy gives you that given a current state of the system, the agent has a probability distribution over the choice of actions. So the agent follows the policy by basically computing this probability density function, and then sampling it to choose the next action. Although this is one of those things where, when I say it's sort of important that the policy be a probability distribution, so during training, there's something they call the explore-exploit trade-off, where during training, if this probability distribution is broad, so if the agent, let's say, has a high degree of uncertainty as to what the best move is at any given point, that sort of helps, because when you're training, you get to kind of explore different paths. When you're actually testing, usually what you would do is you'd take a state, and the agent would look at the probability distribution over the possible actions, and if you're really just trying to do the best you can, you just take the one that's the highest probability. So you just take the best, you pick the best action at every time step. But the fact that it encodes the whole probability distribution over all actions is actually important during training to be able to sort of explore a wide range of behaviors. I call these rollouts, we call them episodes. Basically, you follow a policy, the agent follows this policy, and the environment follows this Markov decision process. And what you get is a sort of stochastic sequence of state, action, reward, state, action, reward, state, action, reward, etc. And then the return is defined to be the sum of the rewards over all time. And this is sometimes people, for simplicity, but sometimes people put out a little discount factor, gamma to the t or something like that to discount future rewards. But for simplicity, we're just using it as the sum of all rewards. Basically, the goal, the reinforcement learning problem, is to determine a policy that maximizes this expected return, where this is saying that this is the expectation value when the rollout is sampled according to the policy pi. If the Markov decision process is deterministic and it's relatively easy to sort of know what the outcome of an action is going to be, then this is more like a planning problem. But in practice, in these problems that people care about, like driving a car or something like that, the dynamics are unknown or impossibly hard to compute. And so all you can do is basically, the best you could do is sort of sample and try to learn what a good strategy is. You can't actually expand the whole tree and try to figure out what is really going to happen, 10 or 20 or 30 or whatever steps down the road. So now we consider a sort of parametric version. So the policy is what the policy is what the agent has control over, pi. And so we give that a parameter theta. And so those are going to be the weights of some neural network eventually. But so then you can think of the expected return as a function of theta. The idea is basically to do gradient ascent on this function. So what you'd like to do is that the goal is to maximize the rewards, the expected total rewards. And so you start with you initialize some random value of this parameter, and then you improve the policy a little bit by bit by moving in the direction of the gradient and out to some learning rate. This is the most basic thing you might try to do to get to a better policy. Yeah, so supposing differentiability, I mean, you can actually compute this gradient. There's a little computation that you can do, and it's equal to this. So it's the expectation of it's the gradient with respect to theta of just the log probability of the action at time t given the state at time t, weighted by the total future returns from that point in time forward. So this is the formula. This is a little formula for what is the gradient of this function. But this is effectively what that means is that even though you're trying to maximize this function j, the gradient kind of looks like that, and it's the same as sort of doing gradient descent on this function. So this is not exactly the thing you're trying to maximize this j. This is not equal to the function j. When I say e hat now, it's become a sample mean over a mini batch. So basically what you do is you can do a bunch of rollouts, and then you take the sample mean of this quantity, and it depends on this parameter theta. And when you take the gradient of that, that will be an estimator for this quantity rather. So even though this function is not really a j, its gradient will be an estimator for the gradient of j. And so you basically can just train your model, your neural network, with this loss function. But that if you try to do this, in most cases, you'll run into some issues. Or in many cases that are a little complicated, you run into some issues. So first of all, I mean, is it clear what I mean by training with this loss function?
Daniel, maybe just a quick comment. So we've had 2 or 3 reinforcement learning talks now.
Okay.
And Adam's talk used the cross-entropy method, which is not the method being displayed here. Whereas this is what some people call reinforce, capitalized. And this is what we saw in Alex's talk last week.
Okay, great. So I'm not sure if they talked about PPO or I'm not sure if Alex talked about PPO or this generalized advantage estimation. So okay, so no. I'm going to okay. When you look at the code tomorrow, I felt like I had wanted to. I mean, it's not actually this. This is like the theoretical thing. You can do this computation. It looks really nice, but this has some issues as a practical loss function when you're trying to do it. So it doesn't have great data efficiency. You can sort of see that, yeah, roughly speaking, what this is saying, when you take the gradient of this, is that you're saying, if this thing is big, then you should make this thing bigger. And if this thing is, from a given state, if the future rewards that were realized based on, in the rollout from that state are large, then the gradient is going to want to make this larger. And if the actual future rewards that were realized were small, then that will have a slightly less upward pressure on that probability. And so that's sort of how you should be reading this. But like there's a whole huge like rollout going on. Like it might be 400, 500 steps. And so there's like a lot of things that happened after this particular action. And so it's like, how do you attribute correctly whether or not this action should really be upweighted or downweighted? This will sort of do it, but it's kind of in a very, very efficient way, like a very inefficient way. So all the information about all the future rollouts, all the future rewards over the course of the rollout gets, makes it basically much noisier to figure out if this is actually a good choice or not. So another way to think about that is that this thing has a very high variance because it's like a sum over lots of sort of lots of random stuff can happen as the thing goes on. Like maybe this was a pretty good choice, but then randomly in 5 moves, the thing made a bad choice, and that's why the rewards are low. So lots of stuff can happen. This thing has this quantity has a very large variance. And the other issue is there's this issue of instability, and we experienced this a little bit. So like I said, this loss function isn't really what you're trying to optimize. It's just has the correct gradient. Practically what happens is that you generate a bunch of training data, you generate a bunch of rollouts, and then you start to do these mini batches and you start to do gradient descent, and you're doing it with this loss function. But after a little while, you sort of get too far from the distribution that was used to generate the data, and the fact that this isn't really the thing you're trying to optimize ends up hurting you. So basically, if the policy drifts too far away as you're doing mini batch after mini batches of gradient descent, you might end up moving to, really hurting the performance. And you can even go into like weird, you can like lose track of what is the best policy really. So it creates instability in the training, the fact that this is not the correct loss function. And this particular function maybe has bad conditioning, because if the probability is small, close to 0, then like log probability is really big and negative, and it's not clear that that's, you can end up moving in weird ways, basically. So in practice, Schulman et al., 2 different papers, basically they replaced this function, RT of theta, and the function psi t with things that capture similar information but are sort of better conditioned. So, psi t.
So, Daniel, can I just ask, when you say Schulman et al., are you saying in the particular case of Grogner bases, there was modification of this function?
No. These are some OpenAI people. There were 2 papers from around 2015, 2016. I really apologize because I was getting these slides together and I meant to include the references, but I didn't quite get. So I'll try to put references into the slides before I share them, whatever. But it's some guys at OpenAI. They were getting little 3D virtual stick figures to stand up and to walk around and stuff like that. It's just different, but it's a general. But they're developing general strategies for addressing these problems in policy. Okay, so basically, generalized advantage estimation. So if you have a value function, this is something that comes up a lot in reinforcement learning. So many of the sophisticated, not like vanilla policy gradient, but the more sophisticated methods. So you have some value, some function of the state, which is an estimate of what your expected future returns are. Then instead of psi of t being the future returns, one thing you can do is you can replace psi of t with an estimator for the advantage obtained by choosing this action at. And so basically that means is like, how much better after doing this action, how much better are your returns than what you expected before you took the action? So a very simple kind of estimator would be to say, well, I have my value function. This is my expected value. So there's my expected value after the action plus the reward that I got for taking the action. And then I should minus this baseline of what I expected my reward, my ultimate reward to be before I took the action. So it's something that you can do. It's not the same thing. It's not appearing, but actually it doesn't affect the policy gradient. It still is an okay thing to put right here. Instead of psi t, you can put an estimator for the advantage. And so there are different kinds of estimators you can use. You could also say, well, I could take my value function at the time t plus k. So I could say, instead of looking at the whole rollout, I could just go k steps into the future, then sort of cut it off and say plus whatever I would expect from there to get for the rest of the rollout. And then I take the key thing is that it's an advantage. It's not the expected future returns, it's the advantage. So it's the realized returns, the difference between what the realized returns were and what you had expected before you took the action. And this generalized advantage estimation kind of does a smoothing of all that. You can do this for any k, and the generalized advantage estimation is a sort of smoothing. There's a parameter lambda, and you sort of just add these all up, an exponential weighted average of these things. And so the idea is that with lambda 0, you just get this very simple. So how much did taking this action improve my value function beyond what I would have expected before I took the action?
Does that assume that the reward is sort of something like sort of continuous? If you do a bit better in the first, like that you sort of keep continuing in getting higher rewards, whereas you could have like a really high reward on the first step, let's say, and then, you know, gradually go down. And so you would choose the wrong policy.
I don't
right?
think so. I mean, no, that because that other stuff ideally it would be captured in the value function. So if you get a lot of reward on the first step, but then after that there's not much, then that would be captured by the fact that the value function here is basically the same as the value function there.
Right. Thanks.
Yeah. If you have a perfect value function and you put this in for psi t, it also sort of gives you the correct estimate. It also estimates the gradient of the j is unbiased. But the point is that, you know, it has better variance. And so it's an example. This lambda parameter it's sort of an example of this bias variance trade-off. So when lambda is 0, you have just this, which is actually a bias estimate of the thing you want in there, the advantage, but it has a lower variance because it only involves this reward here, the single reward that you get on that turn. Whereas when lambda gets very close to 1, you basically get this original thing minus it's still an advantage. So you get the sum of all the returns minus the value of your current state. And so we use two different value functions. So when we use the pairs left, that was okay. So if you just assume that all the pairs are going to reduce to 0, you can sort of estimate, you know, how much longer you have to run the algorithm. But the baseline that really helped us was where you take basically from any state, you can just take the future rollout using one of the silly strategies like degree, one of the simple ones, and then see what rewards degree would have gotten, and then use that as the baseline. It looks a little bit like a supervised, but it's actually not supervised because the thing is not. So let's go back to the formula. If instead of here you put the advantage, so the difference between the actual rewards and the rewards that would have been predicted by your value function. Basically what that's doing is saying, instead of before, where maybe everything has positive rewards, but something have more positive than other, something has more and something have less. Now you're just saying, if it was much more than what I would have expected based on what the degree agent did, I should reward that probability. I should increase that probability. And if the reward that I got was a lot less than what degree agent got, then I should decrease the probability of that choice in the future. So it's sort of, there's a little bit of information being like what, you know, in terms of what the in terms of it's getting access to the information of what its competitor could do in that situation. And then it's trying to say, well, I want to beat the competitor. So you either will increase a choice if it leads to doing better than the competitor, or decrease the probability of a choice if it's less than the competitor. It's not like the agent is actually seeing what degree would choose. They're just seeing how well degree would do in any situation. And they don't actually converge to degree. So they don't end up imitating, but they do end up beating it. So that led to a big improvement in our results, especially this idea of using advantage instead of the naive thing. And then there's also, sorry, now I've lost track of time. So
Daniel, can I just interrupt for a second? You know, I'm kind of like at the same time, like, you know, there's this lovely general framework, and then at the same time, I'm trying to match it with Grogner. And so the thing that I can't match with Grogner at the moment is like, what would the value function, what would be the reward function? So I'm trying to select a pair.
Yeah, so
and then how should I match it?
Great. So yeah, this is actually also a choice. You know, you could choose, so we did number of iterations was one choice, but we ultimately settled on doing the number of polynomial additions. So how many times in the whole algorithm does one polynomial get added to another? And so that captures both the number of iterations, because but it also captures when you actually do a reduction of an S pair, how complicated was that reduction? So sometimes the reduction could take a really long time. And so we just figured that was a better proxy for the actual, like, the goal is for computational, complexity or whatever. So we decided a better proxy was this polynomial additions thing. But that's basically all there is for binomials. But if you have non-binomial ideals, then you might want other things too, because you might want to penalize having really, really long polynomials around. So because there, it's not just the number of polynomial additions, the number of terms in the polynomials will affect your computational time too. But for our purposes, we just did number of polynomial additions, which captures both the reduction and the number of iterations. So this other, it's also by Schulman, a different paper by Schulman et al. And one was when he was a student at Berkeley, and then he went to OpenAI and wrote another paper. And basically, this function has, I have to say, I understand this less well. It feels like more of an art than a science. But then, you know, instead of this function, instead of this function right here, it's better to, they say, replace it with the ratio of the probability of the current. So remember, you have some choice of parameters, you generate a bunch of rollouts, and then you start to do gradient descent for a bunch of mini batches on the parameter theta. And so this ratio is maybe a better conditioned thing to try to do gradient descent on. And it captures roughly the same thing, like, you know, is there an upward pressure or downward pressure on this probability? And that's captured if you put if RT of theta is this, or if you replace RT of theta with that. And then in addition, they do this clipping thing in PPO where they take the advantage estimator from the previous slide or another of your favorite advantage estimators, and they say, they do this kind of clipping. So effectively, if the advantage is positive, then you know, this RT, which is, it can't be too far from 1. But if the advantage is negative and the RT is very, very large, that can be penalized. But otherwise, you want to clip the RT so that it's not too far from 1. And then also you stop training if the new action distribution sort of drifts too far away from the original one by KL divergence. So this is all, the whole point of this thing is to get it to not, the training becomes unstable if during your epoch, like the policy function drifts too far away from what it was trained on, and then it can start to do kind of weird random things. It can move in a random direction. And so these are both methods to try to say, don't let the policy move too fast. Don't let the policy move too fast. And we did find that this, what?
I was going to ask, I mean, you didn't penalize the size of the coefficients.
Which coefficients?
In your polynomial.
No, right, we did not. No.
So,
well, because we were in a
because that was
field.
one of the other advantages that you mentioned.
Yeah.
Yeah, I see. And so it doesn't. So I guess it doesn't. The bit size of any two numbers is kind of the same.
It's the same. Yeah. Right. So for finite, so I forget, if you were going to do this in sort of more general setting, then you'd probably also want to have a penalty for the size of the coefficients. You want to just find a good proxy for whatever the thing you're trying to actually minimize, like compute time or something like that, or memory, you know, whatever it is. Yeah. Anyway, so this is another more of a sort of a trick where you basically just replace the function that you had this beautiful derivation, and then you just completely replace it with something else that kind of works a little bit better. So it's like an engineering solution. Anyway, so, okay, so to summarize before I talk about the actual results, so Grogner bases, there's special sets of polynomials useful for many computational problems. So Buchberger's algorithm computes a Grogner basis, and its performance depends on selection strategies for the pairs. And then at the same time, there's this general reinforcement learning framework for learning these kinds of, you know, complicated interactions between an environment and an agent. Yeah, and policy gradient methods allow you to sort of iteratively improve parameterized policy functions by doing a kind of gradient descent. Okay, so now I'll tell you about the results. So as you've been guessing, as I've been speaking, this is the model that we have in mind. So the environment is a Buchberger class, and it basically implements the algorithm. And so you start with a generating set of polynomials and a set of pairs. That's the initial state of the environment. And then that initial state gets sent to the agent along with, I guess, the initial reward 0. The agent selects a pair and sends that information back to the environment, tells them I select this pair, and then the environment runs through Buchberger's algorithm. It removes the pair, reduces the S polynomial, and updates the generating set if necessary. And meanwhile, it counts up the number of polynomial additions it performed, and it sends that back as the minus that as the reward. So it's a negative reward. And then at the end, the environment will spit out the Grogner basis. So this is very naturally a reinforcement learning problem. And so, as discussed above, most of our experiments we stuck to binomial ideals. So S binomials with no constant terms. That's again is sort of to avoid this complete intersection business. And n variables, maximum degree D. We had different options that we experimented with. So uniformly at random for the monomials, weighted by their degree, so that basically every degree was equally likely, or only of the maximal degree, which was the homogeneous one. And I don't know, it's nice. By adjusting the degree and the number of generators and stuff, you get a whole, playground of different problems of different difficulties. But it does leave this question, and actually is how should you actually represent the state of the system to a neural network? And I think that's one of the most interesting aspects of this problem sort of going forward. But, this is very interesting from a reinforcement learning perspective also, because the number of actions can change and grow quite a bit over the course of the thing. So the number of actions is not constant, and nor is the size of the state is not constant, because the list of pairs can get larger and larger. And so and also if you have general polynomials, like how do you even represent a polynomial in a way that a neural network can read it and make something meaningful out of it? So a lot of that stuff we have not, that's in iteration 2 of this project. That's sort of still active. I'm sort of still messing around with it, but I don't have anything fantastic to report about that. It's a lot of these questions. It's a very interesting question. And in this proof of concept, we just simplified our lives quite a bit. And basically what we said is, well, every pair. So first of all, we ignore all coefficients. All we care about is the actual exponents of the monomials. Basically we say, take our set of pairs, and for each pair, that's 2 polynomials. We choose a number of lead terms to keep. So most of the time we take k equals 2, which is all that we really need for binomials anyway. That's the whole thing. And then so so each monomial its exponent is an n-dimensional vector. And so here, so if with 3 variables, k is 2, or we're in the binomial case anyway, it doesn't matter. So you take the 2 lead terms of every pair. So then you have these, let's say that, here's some generating set, and here are some examples of what a pair set might look like in the course of running the algorithm. So basically, let's see, F1, F2. So that's 160, that's that monomial. Then 024, that's that monomial. And then F2, so 004, that's that monomial. And 001 is that monomial. So that's the way we decided to encode our pairs, as just the list of exponent vectors of the k leading monomials of each one in the pair. And now the number of rows in this matrix is the number of pairs, and that can grow or shrink as needed. But once you've decided on k and the number of variables, the number of columns in this matrix is always the same. And so that's actually a kind of thing that you can feed a neural network. They're really, if you take basically a convolutional sort of neural network, and you can just run it over. So basically the way our model works is the following. You take this matrix, so it's the number of pairs times this 2kn, which is the vector that you need to represent the exponents of the k leading terms of the pair. There's a very, very simple there's some number, there's a single hidden layer roughly, and you you do a 1D convolution with ReLU activation to get some hidden parameters for each pair. And then you do another 1D convolution linear, but basically you just take now a linear combination of those parameters to get, at this stage, you'll have just for every pair a number, and then you softmax. And then you take softmax to get that number, basically they're called the logits, and you take the softmax, and then you get your probability vector over the set of pairs. So effectively, all it's doing is it's doing in parallel. It's just doing a very, very simple two-layer neural network on each of the pairs, on the vector, two-layer fully connected neural network on each of the vectors corresponding to each of the pairs. So at this point, every pair just gets its own value, and then you softmax to choose to get the policy. So it really is the simplest thing. No context is taken into account. So this model will, if you give it a pair, it doesn't matter what the other pairs look like or what the generators look like. It just spits out a number, which is like, how good is this pair to choose? And then you softmax those numbers to get your policy. So it's a very, very simple model.
Daniel, so I'm just a bit confused by you saying conv. So it's just a fully connected vanilla.
It's fully connected, although it's conv. It's fully connected. It's implemented as a 1D convolution because it's you can think of it. I think it's a convolution with a kernel of size 1 in the row direction. You're just applying the same. The row direction is what I'm thinking of as like the number of pairs. So it's like a 1D convolution with the kernel of size 1, where it takes this 2kn linear space to an h linear space, and it does that at each row.
Oh, the same thing at every, okay.
It does the same thing at every row. Yeah. So it's implemented as a 1D convolution. But you could also just think about it, I don't know, however you want to think about it. It's sort of silly to call it a convolution, but that's what it is, how it's implemented. Right, because the kernel has size 1. Yeah, so basically the policy network is initialized randomly, and then training, we use PPO, and in each epoch of training, we do 100 rollouts of the current policy network. Then we do this computing the future rewards, and we use, instead of just using future rewards, we use generalized advantage estimation using a degree model as a baseline. This is just reviewing what I mentioned before. And then you use this multiple steps of this atom optimizer on this clipped PPO surrogate loss, and you do early stopping using KL divergence. A lot of tricks in there.
Dan, so when you train it, you basically then tell it that you know of certain pairs that lead to an efficient procedure in the algorithm, or?
Yeah.
The question is, I mean, for your training data, it's basically about the training data, right? Because you have all these pairs, and then you need to give some weights, right, to different pairs. Which pairs you think are good pairs, or which pairs you think are bad pairs, right?
Yeah, yeah.
And so that comes from having already run Buchberger's algorithm and knowing basically on which pairs it performs efficiently.
No, it doesn't. It comes just from the. You don't actually. It's a very indirect. I mean, the loss function. Yeah. The loss function is like this. So that this pi theta is the thing that's the neural network, and it takes you start with some state. So the way that TensorFlow works is that you have some incredibly long computational graph, and at the end you just have this function, and then you have the auto gradient, and you just take the gradient or whatever. So it's not quite as explicit as what you're saying. You don't need the data of which moves were good moves and which pairs. I mean, you definitely don't have any information about which pairs were good and which pairs were bad. All you have is so the training data is generated, is simulated, and that's the step 1. In the beginning of every training epoch, you take the current policy network and you just interact it with you just generate a bunch of random ideals and you see what the agent will do when it's interacting with this environment, see what rewards it gets. And then you smush all that together into this sort of giant function, ultimately. And then you take the gradient of that function with respect to the parameters of the neural network, and that tells you how to change the parameters of the neural network. And then you do this a bunch. It's stochastic gradient descent, so you do this in mini batches. So you do this a bunch of times, and then there are some tricks where you to stabilize this training process so it doesn't drift too far from the original policy network. So you do this a bunch of times, this gradient descent step, and then eventually you stop. You have a new policy network, and you start all over again. So then again, you generate a bunch of new training data where you just watch how the policy network interacts with the environment, and you see what the rewards are, and then you do the whole thing again. Does that make sense?
Yeah, I see. Yeah, because you select pairs, then you give them back. You apply reduce in, don't know, Macaulay or something, right? And then you basically see whether the degree went up or down.
It all happens actually in, it's all implemented, well, it all has to be implemented in TensorFlow, because sort of TensorFlow has to see the whole, it has to see the whole process, but I guess.
Oh, because you're counting the number of operations.
Yeah. Right, so the kinds of things for the paper, I'm going to try to get a smaller, so you can actually run it tomorrow and actually do the training on a smaller sample. But so this is what it looks like, and you have to have graphs like this in the machine learning talk, where you have the training. So these are a bunch of like standard selection strategies. This is the silly one where you just take it in the order that they appeared. Then there's degree, which I mentioned. There's normal, there's sugar, there's similar ones. Random is like where you literally just use a random pair. And pretty rapidly, this is in 3-20-10 weighted. Weighted means that it favors lower degree monomials appearing. So it's a little easier than the 3-20-10 uniform. So yeah, the numbers are a little different here. Yeah, so 3-20-10 uniform is just a bit of a harder problem, but still fairly quickly the agent gets down to doing better. This is during training. Then we did a little bit of training on this much harder problem, and it's sort of going down, but it's not quite as fast, but it does actually get better. It gets lower. Yeah, no. Maximum is also pretty hard, but in any event, here's another example. So this one is sort of weirdly degenerate. Okay, so yeah, so here's like just a table of results that we got. So again, here's a first degree. Normal is where you take the LCM of each pair, the LCM of the lead monomial of each pair, and you take the one that's highest in the monomial order. Whereas with degree, you just take the one with the highest degree. So they're pretty close. They're very similar strategies. Then there's one sugar, which is like sort of you homogenize, and anyway, another standard strategy. But so the takeaway is that the agent, this is in a nice 3-20-10 weighted. The agent does better. It does. This is one of the better domains. But the harder domains, the improvement in performance was smaller. But another important thing is that the drop in variance. So here I have a graph here. So this is the 3-20-10 weighted distribution. And so this is if you just take 10,000, I think it was 10,000 ideals randomly, and just say how many polynomial additions did it take to reduce each one using the different selection strategies, you'll see that some of the tails really shrunk down with this thing. So that's promising. It's much narrower, and in addition to having a higher peak. And then we did a little bit of discussion about how this generalizes. So unfortunately, this model, once, like I said, you fix the number of variables and you fixed K. So if you go back to the model, this thing is very much fixed. When you're learning, this is learning a matrix to take a 2kn vector into an h-dimensional vector and then to a one-dimensional vector. So when you're training the model, you cannot apply the same model to something with a different k or different n. So in particular, there's no easy way to test a model that's trained on on n variables for a higher number of variables. Although I have my own, I have some ideas about how you might try to generalize in that direction, but at least the way this model is designed, there's no easy way to test it. But you can easily change the number of degrees in generators, and you see that it's not terrible. This is the ratio of the agent performance to the best benchmark performance in this distribution. So the agent was trained right here with this, the degree 20 with 10 generators. And then if you increase the degree, it actually does, also does fine. If you go, it does a little bit better against the agent. So in this direction, it's even doing, so it's actually doing better in this direction than where it was trained, oddly enough. And it, if you go up to 22 generators, it's still like doing pretty good against the agent. It stops beating the agent sort of at this, at the frontier here, is where it sort of stops beating the agent. So you have to go, but it is interesting that actually as you increase the degree, generalization seems to get better, at least when you're comparing the ratio. So there's the ratio of the average number of polynomial additions for the agent versus the same for the best benchmark. And so again, with this generalization question, we did this thing where we took a Poisson distribution. So you can again, once you get rid of the binomial thing, you have a philosophical question, which is like, what do you even mean by a random ideal? So just for fun, we said, okay, well, you can have a binomial, and you can imagine this being then sampling with a Poisson distribution for the, should there be a third term, or should there be a fourth term, or should there be a fifth term? And so it's another way to get it's another way to sample sparse polynomials. So I didn't want to lose the sparsity because, then you probably end up with complete intersection. So like, let's consider polynomials that appear in nature, let's say, have relatively few terms. And so you have this parameter lambda, which is controlling how many terms on average your polynomial has, starting with 2. And the thing is to see here is that in the median, so the median, it still does okay. I mean, it goes out to at least with, so at this lambda is 0.3, like most of the polynomials are still binomials, but you do definitely have a few trinomials or polynomials with 4 terms in there, and it's still doing better than the best benchmark. But then as lambda goes up, it gets worse. And then here, it does worse, even with a little bit of, even with a once in a while having a more than binomial in there, it does worse than the best benchmark in mean. So it's interesting. I think it's an interesting direction. When you plot the graph, I didn't include it in here, but there's a really weird thing that's going on when you try to generalize from binomials to non-binomials. There seem to be like some really bad cases, and maybe there's a way where you can sort of detect and avoid those really bad scenarios, and take advantage of some of this generalization in here. So right, so this is the thing I mentioned at the very beginning. So we actually said there's a high correlation between the agent's preference score and the true degree of an S pair, where this is the new selection strategy that we were not aware of any implementation that actually uses this selection strategy, but it's a pretty natural one where you take the S polynomial and just take the degree of the S polynomial. And in fact, there's like quite a lot of correlation between what our network, the sort of preference score for a pair, and this true degree thing. So we just discovered this by experimenting. Dylan was just experimenting and trying to figure out what the heck the network was doing. And because it's such a simple model, you can just do that. You can just feed different polynomials in there, and lo and behold, it was this. So when you go back to the generalization question with lambda, so I mentioned there's this kind of funny, weird tail behavior. So, our model being so far out of distribution, it sort of leaves the region where it's trained. But when we discovered this true degree idea, it now continues. If we now just do true degree, so basically we discovered this thing that it looks like the model was doing, highly correlated with this simple rule, and this true degree thing really does outperform for these sparse polynomials that are no longer binomials. It outperforms the best benchmark that we knew about before. So in a practical sense, I guess you could say the paper, we discovered this kind of yet another simple heuristic, but it's not human designed. It was discovered by by a reinforcement learning agent. And it seems to outperform, at least with these. Now, this is no longer just binomial. This is now in the sparse, but still in in this relatively simple setting of 3 variables and things like that. So still is a toy model, and I have no idea how well true degree does, like as a general, holds up as a general strategy. But this suggests that might be something to look into. To summarize, I think I'm basically done. So yeah, so basically we can express this pair selection as a very, very natural reinforcement learning problem. And if you focus in on these, on domains where it's actually trainable, so that's kind of the issue, is that, you need to generate thousands, hundreds of thousands, millions of these examples where you've completely done the ideal. And so you have to stay in some domain where that's feasible. And so, but in this domain, this binomial domain, this very simple model does outperform this sort of state-of-the-art human design selection strategies. And generalization presents some challenges, but I think that the whole point of this project is to sort of suggest that there's something here, and that maybe with more sophisticated models for machine learning, we might be able to dramatically improve the performance of this algorithm and other algorithms in computer algebra. So I think I'll stop there. I have a little bit more on like other future directions, but I think I'm sort of out of time, right? So yeah, so I'll just stop there. That's a pretty good stopping point. Thank you.
Thanks heaps, Daniel. This was fascinating. Questions?
I just had one question on one of the last things you talked about with the true degree thing. Can you use that to sort of bootstrap the training of the machine, or does that not really yield any additional like improvements?
Well, the only way, I mean, I could imagine using true degree in the value model. So we had this value function. We did some experiments with that. I don't think it really mattered that much. What the, I think the biggest thing of the value function is that you're estimating these future rewards, and they're centered around some enormous number. But then when you have the value function, you can sort of recenter them around 0. And it just gives you a clearer signal of like, this is better than expected or this is worse than expected. But when we were doing experiments, the specific, so yeah, I think I have some here. Oh yeah. So we did some experiments with value models, learned value models, including, we also did experiments with different agents instead of degree. So this is the value model that just uses degree. But we also used some neural network value models, and they did okay. Yeah. So this is the difference. If you use no value model at all, this is what you see. And this is what you see if you use some value model. But the differences between the different value models were not very pronounced. So I don't recall if we specifically tried true degree instead of degree here, but I wouldn't expect that to make a huge difference.
Okay.
We even tried, I think we tried it, yeah. You might also ask, you could like bootstrap with itself. So you could use as a value model its own performance from a few epochs ago or something like that. But that became too computationally impossible, basically, because like it's not like, I don't know.
Right.
Yeah. Every time the value function is called, you have to do a complete rollout with this neural network model, which itself is not like, it's a kind of a, that's the other thing behind this, is that this is not a production thing. True degree has potential to be a production thing. But these are pretty big matrix multiplications, not huge. I think 128 hidden parameters is what we used. So it's not huge, but it still is quite a lot of matrix multiplication to do your pair selection. And so another pressure on this is that whatever selection strategy you, in practice, like if this is going to be practical, you need the model to be somewhat small. Because you're going to be doing this pair selection again and again and again in the middle of the algorithm. So whatever benefit you get from choosing pairs well is offset by the amount of computation you needed to do for the pair selection itself. So
right. Okay.
but I consider that to be translational. That's like down the road a little bit. Like if we get something that if the next generation of this is a factor of 10 improvement or something, then there's maybe some room to, have a more complicated model. So we're trying to figure out what is possible. The other thing is, yeah, we did this kind of funny experiment where you can just do a rollout on every ideal, like, do it 100 times and you take the best one. So you just randomly roll it out and do the best one. And that does better than our agent. So there still is, so this basic question, is there more to this problem? And the answer is definitely yes. Like if you just take these ideals and just do a random search, you will find a particular sequence of choices that was substantially better than even what our agent could do. And so I think that a really interesting question is to use like tree search or something like that. You know, more advanced methods of expanding this tree and searching for the best, you know, the best policy. But anyway, there's a lot to do, a lot more to do.
I have a few questions and comments.
Okay.
So just first to the comments. So one of the things that I've fallen in love with recently is like equivariant neural nets. So for example, like at the moment, you take a whole lot of pairs, and then you produce a probability distribution on pairs for which one you should take. And you want that to be equivariant. Like if you reorder your elements, you would hope that your probability distribution reorders in the same way. And like my understanding is that you can kind of get this equivariance in two ways. One way is data augmentation, where you just like give it enough stuff and then it sees, kind of learns the equivariance, or you can like bake it into your neural net. I don't know, recently we've had a lot of fun and also sometimes success with like using things like deep sets and stuff like that to put, like attention is a version of that. And I saw that on it.
In the very, very simple model, it's automatically equivariant because it's just doing this basically computing a number for each pair. But in the, we did play around a little bit with models. I think that in some sense you'd like to use context from the other pairs of the generating set. And in that case, equivariance becomes an issue, right? And then you can do these different things. Yeah, I think that's right. I definitely think that something like that, that's what I've been pushing my students to try to investigate, is if you can, in that direction, using context, then you encounter these issues of having it be equivariant.
And like in a more like
for you, there's a second. Yeah. Can follow up on the equivariance.
Sorry, Stefan. I'll just continue for a second. So, and there's more sophisticated invariants. Like you could imagine some kind of invariance in your polynomial generators. So you have some symmetric power or something, and then there are methods now to make the neural network equivariant under those kind of actually invariant under those kind of operations. And the other thing that's like remarkable with deep sets is that you train a model, and then it has input, let's say n, like n vectors or something, and it makes sense to put in any number of vectors into the model. And so you kind of, like you were talking about the fact that once you train this model, you can't naturally scale it in any of your, either your k or n directions. But with like equivariance often has the effect of also making that scalable. Usually the performance is hopeless when you change to different n, but at least the question makes sense.
That's interesting. That's really interesting. Yeah, I'll think about that. Thank you. Yeah, equivariance in terms of, you have a symmetric group acting on the variables, but you also actually have like a general linear group. Of course, then you'll leave leave binomials, but it's, yeah, but I don't know, maybe that's an interesting, yeah, it's very interesting. Yeah.
The other question that I was wondering about, so your true degree was basically found by essentially staring at plots. And one of the successes in the knot theory project was actually looking at a saliency plot of everything that could be possibly related to the problem and trying to see which of those variables correlate with the, in your case, the agent's actions. So I was kind of wondering if true degree is an approximation of something that actually involves more terms, which you could potentially find by some kind of saliency analysis.
That's interesting. Yeah. Basically you're saying do a regression or something like that. I'm not sure. Like I said, it was sort of Dylan Dylan had discovered that by, I guess he was just curious as to what it was doing, and he was basically doing a regression. Doing a correlation is doing a regression one variable at a time. I don't know that he did several, because you could throw a degree, you could throw all the other ones in there too and see which gets the largest regression coefficient. Yeah, I don't know. That is cool. Yeah, I don't really know. Or just you could throw everything in the kitchen sink and just say, any kind of plausible. I mean, you still somehow you need to a human generated like plausible heuristics for this if you're trying to come up with something interpretable. But yeah, that's a good point. I don't remember him actually doing it that way. I think he's just like was curious about true degree.
Maybe just one final thing that we like, this is just another thing that we had a lot of fun with and, you know, might be interesting, is that like sometimes in order to try to get an interpretable model, you can do this thing called like distilling a neural net or teach a student, where you like have a complicated model and then you try to get a simpler model to learn what the complicated model does.
Right, like model reduction stuff I've heard it called, I think. Yeah. You do supervised learning basically with the, you do supervised learning for the small model, for the large model. Yeah, I think that's, I definitely think that that's plausible. Yeah. I mean, the real issue is that we don't really have, oh yeah, I should have said that increasing the size of these models in this domain did not really substantially improve performance, which is what makes me think that, I think for this problem, what you really need is a different architecture, one that does sort of attention, uses attention mechanisms to try to take context into account, or like a Monte Carlo tree search, like an AlphaZero kind of architecture that really does a little bit of, I mean, it doesn't seem like there's more that you can do by just looking at a single pair and saying, how good is this pair? At least like we made the networks deeper, we made them wider, didn't really affect the performance in this domain. So the model reduction thing will come, if we get one of those other things to work actually, then yeah, eventually we'll probably want to do a model reduction and come up with, find the minimum, the smallest model possible. But that's all hypothetical because I don't really have like a big complicated model that does fantastic yet. I mean, I think that would be cool to find to do an AlphaZero kind of thing that can then get like an order of magnitude or more of improvement on this, in complicated domains. So yeah.
One thing that just blew my mind last week in Alex's talk is that what they did at some point is they had like this AlphaZero, like super AlphaZero that's performing at like ELO 5000 level, which is like very superhuman. And then they trained a supervised model to try to just predict the next move, like predict the policy network. And no matter how far they trained this only got to like 3000 level, which is like bad professional.
Oh, interesting.
And so like that difference between 3000 and 5000 is the difference between like, supervised learning with essentially perfect data and Monte Carlo tree search.
Yeah, it's interesting. I mean, it sort of makes sense. Like without doing any tree search, how would you, I mean, it's asking quite a lot of a model to just look at this and then to predict how the entire rollout is going to go. I mean, it's crazy. It's asking a lot. Yeah. I bet even just doing a little bit of tree search helps, because you go like 2 or 3 moves in and you realize it wasn't such a great move in chess or in Grogner based and stuff. So yeah, that's interesting to hear that. That was sort of my intuition too, that tree search was a good direction to take this project in.
Thank you so much, and see you all soon.
Thanks for your attention. Thanks for the invitation. This is really cool that you guys are doing this.